Okay, my friends, in this last hour, we are just going to expand our knowledge about the looping mechanisms. We are just going to embed loops inside of each other. And this problem is the problem that we have mentioned earlier. What is the limit of the ratio of the last element of the Fibonacci sequence to the previous element? We want to see that where this goes. If you remember, so let's just see, if you remember, I have already mentioned that the ratio of the last element to the first for the first two Fibonacci numbers is infinity. 1/1 is 1, 2/1 is 2, 3/2 is 1.5, 5/3 is 1.67, so and so forth. It goes like this. I mean, it is mathematically, it can be mathematically shown that this sequence, the ratio of the last element to the previous element in the Fibonacci sequence, converges to a certain value. The values are just going to get closer and closer to each other, but in not a damping sequence. Okay, as you can see, infinity to 1 decreases, so from 1 to 2 it increases, from 2 to 1.5 decreases, then it increases, then decreases, then it increases again, then decreases. So in an oscillating manner, the values are just going to converge to a certain value, and we are interested in calculating that value in the end. Okay, what is the limit of the ratio of the Fibonacci sequence to the last element to the first previous element? Okay, that is the thing that we are interested in right now. Okay, now it can be mathematically shown by proving the statements. Okay, so the difference between the last ratio calculated to the previous ratio in absolute difference is always less than the absolute difference between the previous ratio and the ratio that is evaluated previous than that one. Okay, this is the mathematical part of it. We are not going to show that. This is not the context of our course. So we know that this ratio Fn/Fn minus 1 converges to somewhere. And we are interested in calculating that point where it converges to. Now, this is the flow chart that will help us to calculate that limiting ratio of the last element to the previous element of the Fibonacci sequence. First, we need to define a reasonably small epsilon value. So this epsilon value is going to be our approximation error. Okay, approximation error. So we are going to check the difference, absolute difference between the last two ratios that are calculated between Fn and Fn minus 1. If that ratio for the last two calculation has a very, very small difference than epsilon in absolute value, then we say that that approximation is a good approximation. So we can, or while loop can terminate. So first, we set the first zero index of the Fibonacci sequence as 0 and the first index of the Fibonacci sequence as 1. The next number that we are going to calculate will be at the second index. And we define another variable that is called R, which stands for ratio. Okay, it stands for ratio. Right now, we only have two elements in the Fibonacci sequence, and the ratio of the last element to the previous element is 1/0, which is infinity. Therefore, the ratio is currently infinity. Then we say, calculate the next Fibonacci number, Fn, as the last summation of the last two numbers. Then we set another variable that is called R new, ratio new, the new ratio. Okay, the new ratio as the new ratio that is evaluated by taking the ratio between the new last element that we have evaluated to the previous element. Okay, now in the first iteration, R will be infinity, R new will be 1/1, therefore it is going to be equal to 1. Then we enter inside the decide module here, the diamond shaped component of our flow chart, and we check the absolute difference between the new ratio and the previous ratio. If that absolute difference is less than or equal to epsilon value, which is reasonably small, in that case, we return the last ratio that we have evaluated as our result, because we will see that when this condition is satisfied, when the last ratio that is going to be calculated is no different than the previous ratio, or the difference is acceptably small, in that case, we say that the convergence has almost occurred, and we can return the last ratio between the last two elements of the Fibonacci sequence. Otherwise, if this condition is not satisfied, if the difference between the last two ratios that is calculated is not very small, in that case, we update the ratio as the last ratio that we have evaluated. And we update the next index that is to be evaluated as m+1, which is going to be the third index for the first iteration. Then we evaluate the third index of the Fibonacci sequence, and then we again evaluate the new ratio, which is the ratio between the third index and the second index, which is just going to be 2 this time. And when we check the difference between 2 and 1, the absolute difference will be still greater than the epsilon value, which is reasonably small, if you remember. And it will continue to loop itself again and again and again until the last two ratios that we have calculated will eventually be close to each other than the epsilon value that we have defined as an input. So this is the program which helps us to do that. Let's see that in action. First, I asked the user to enter the epsilon value. This time I convert that epsilon value to a float because that epsilon value is going to be a very, very small value, just like 0.000000001. Okay, or we can create it scientifically as 10 to the power minus 12. Okay, 10 to the power minus 12. Now I say my previous number is 0 and my last number is 1. Right now I have two Fibonacci numbers that I evaluated. And then I say my ratio right now is a value which is close to infinity. Okay, a sufficiently large value to represent infinity. Right now, there is no way for me to represent infinity, which we are going to learn later on. Also, you can download some packages into your program to represent infinity values. However, at this point, I need to write here a very, very large number for the current ratio, which is 1/0. And that is a very, very large number, like 1 billion. Okay, 1 billion. And there is this loop counter. In this loop counter, we are just going to count how many times the while loop is going to repeat itself again and again. And I say I create a while loop with a true Boolean expression, which means this expression is not the driving force of the while loop. It will not break us out of the while loop. It will only continue whenever the loop repeats. And I say, whenever I enter the loop for the first time, I increment the loop counter with 1. Okay, so this is my first entrance to the while loop. So it will be changed. The loop counter will be incremented from 0 to 1. And then I evaluate the next number in the Fibonacci sequence as the summation of the last two numbers. And I define the new ratio between the last two elements. Next number divided by the last number. Okay. The previous ratio was between the last number and the previous number, which was infinity. And I also define a variable R, which stands for error. Okay. I define a value error here. And I say it is going to be equal to the absolute value in the difference of the new ratio and the last ratio, which will be currently 1 minus 999 million something, which is going to be very large. And then I write an if statement. If the error, if the difference, absolute difference between the last two ratios that I have evaluated is less than or equal to epsilon, then break out of the while loop. Okay. Otherwise, do not enter this if statement. Then update the previous number as the last number and the last number as the next number and the current ratio as the new ratio that you have calculated. Okay. Then go back to the beginning of the while loop again. It will automatically enter the while loop because the while loop is driven by a true Boolean statement at all times. There is only one way to break this while loop. Whenever that error is calculated to be smaller than the epsilon value that the user has entered. Okay. Once it gets out of the while loop, the output message will give us the ratio of the last element of the Fibonacci sequence to the previous element. There is a new line here, converges to a placeholder here we have in the F string, R new, which is going to be the last ratio that we have evaluated. Okay. And after printing this output message, I print another output message it writes desired approximation is observed at iteration loop counter. So it will also return us how many times this while loop has been repeated until the desired convergence has occurred. Now let's run this. It says enter your acceptable approximation error. So I'm just going to write a very, very small approximation error here, like 0 to the 0.0000001. Okay, 1 divided by 1 million, simply. Now I press enter. It says that the ratio of the last element of the Fibonacci sequence to the previous element converges to 1.6180338 something. And the desired approximation is observed at 17th iteration. So it's been only 17 times that this while loop has been repeated to get a absolute difference between the last two ratios that have been calculated to be less than 1/1 million. Okay, so that was a very, very short one. Now let's rerun it again. This time I write a scientific number here. That scientific number, my friends, means 1 times 10 to the power minus 12. This is not the Euler number that I write here. E is not the Euler number. It is 1 times e to the power minus 12, means 10 to the power minus 12. Now, when I press that, it says the ratio of the last two elements of the Fibonacci sequence is 1.6180339, which is not very different than the previous number, but you can see that after the 7th decimal digit, there is a difference after the 7th decimal digit. And this time the desired approximation has been observed at iteration 31. My friends, this value 1.618, so let me show that on presentation file now. This value 1.6180338 something, that value is so-called the golden ratio as we know it, okay? The golden ratio. You can read about the golden ratio. It's a mathematical constant, and it's a very, very important mathematical constant, even for industrial engineers, okay? Because in numerical analysis, there is a method which identifies the minimum value of convex functions. And that method is called the golden section method, golden section, which bases its calculations on the golden ratio that has been evaluated. Okay, so therefore, do not think that golden ratio is just a magical number for only people who are just fans of mathematics, okay? It is not something that is so magical to impress people. It is a very, very important mathematical constant, especially for industrial engineers here, because there is this method which we are going to teach in the next module, which is called the bisection module. The golden section method is much more efficient than the bisection method in computational complexity, and it bases its calculations on the golden ratio that has been evaluated here. So this mathematical constant is a very important mathematical constant for us. Okay, now, my friends, we can also use while loops to correct user inputs to prevent exceptions in undesired program crash. Now, please be careful. In this program, I asked the user to enter an approximation error. Obviously, the user must enter a value which can be convertible to float here. If the user writes, "I'm Batman" here, then the program will crash. Okay, if it writes something as a string or if it writes a list here, the program will crash in the beginning before entering even the while loop. Therefore, we also need to make users to enter the correct inputs according to the questions there. Until they enter the correct input, the program must put the user into a while loop until a correct term or correct type of information is entered, okay? Now, we are just going to do it here in this while loop 0.05, okay? So let me show that here again. I say there's a while loop here which will repeat itself infinitely many times. However, there is a break statement here which will eventually help us to break out of the loop. And I say this while loop will try this code block first. It will try this code block first. However, during this code block, if we get a value error by the user, okay, the user may not enter an input which is convertible to an integer here, then we get a value error, except we have a value error. In that value error, the user will be informed to provide an integer. And the while loop will repeat itself, okay? So we say try to get an input from the user by asking to enter a positive integer. The entered value will be tried to convert it to be integers, and it will be assigned to a variable user number, okay, associated with the variable, to be associated with the variable user number here. However, if the user somehow enters any input which cannot be convertible to integer, we will get an exception of a value error, which will immediately direct us to this exception code block. The user will be asked to provide an integer. The while loop will repeat itself, and the user again will see that input function to enter a positive integer. If user number is less than or equal to 0, then I write, now let's just assume that the user has entered a numeric value here, which can be convertible to integer. If the user number value is less than or equal to 0, then I write print, please provide a positive value. Because in this program, I especially ask the user to enter a positive integer, okay? If the user enters a negative value, the user will see command line here. And again, the while loop will repeat itself, okay? Because we enter in the if block here, not the else block. And the loop will terminate and come back to the beginning of the loop again. However, if the user really enters an integer, my friends, which is positive, okay? In that case, we say that break out of the while loop, and we will simply print your number is the number you have entered, the user number that you have entered, okay? Let's run this. It says enter a positive integer, and I write I'm Batman, okay? It says please provide an integer because the value order has been happened, okay? The try code block experienced a value error, and it has directed me to the exception block, and it has warned me to provide an integer. Because the while loop repeated itself, again, it asks me to enter a positive integer. This time I enter a negative value, -2. And this time it writes me, please provide a positive value. This time it does not enter the except block because this is not a value error that we have experienced here. This is just a logic error because the user has not followed the instructions, okay? However, -2 can be converted into an integer. However, it is less than or equal to 0. It is not a positive value. This time the program is warning us to provide a positive value. Now, if I enter a positive integer like 56, then I get my number as 56, and the program terminates. So we can use while loops over a user until the user enters the correct input in our descriptions, okay? So this program basically forces the user to enter a positive integer. Unless the user enters a positive integer, it will keep the user in the while loop. However, my friends, there is this flow of this program, which is also a logic error. If that user enters a float number, this int function will convert it to an integer. I think the integer part of it. No. It cannot convert it to an integer. So it says, please provide an integer again. It still gets a, value error here. However, if you do it like this, so only integer strings are convertible to integers, as you can see. If you write a float strings are not convertible to integers. However, if you do it like this, first the input will be converted into a float, then the float will be converted into an integer, okay? I think there is an error here. Why? So integers. So let me do it like this. Float. Now it's correct. Okay. Now let's run our program. Enter a positive integer. If I enter 3.14, your number is 3, it will say me. Because first I have converted the string into float, then into an integer. So that's a problem here. So these kind of things can be complicated a little bit. Do not do that. If you take an integer in the string format, only that can be converted into an integer. Okay. If you enter a string with a float format, it cannot be converted to integer, as you can see. All right, let's move on. So you have different cases here. If you enter I'm Batman, it says please provide an integer. If you write a float there, it again says provide an integer. If you enter a 0, which is not a positive integer, it wants you to provide a positive value. If you really enter a positive integer there, then the program will terminate and say your number is 20. Okay, now just like we can nest for loops inside one another, we can also nest while loops inside one another. Okay. In fact, you can nest for a for loop inside a while loop inside a for loop. You can nest if and else statements or try and except blocks inside while loops, for loops. So this kind of nesting is not limited to 2 levels. You can, by this idea, basically, by nesting different loops in each other, by nesting if blocks, if else blocks, if else blocks, try except blocks inside one another, my friends, you can create a very, very complex program, my friends. Okay, we are just going to see the next example in which we are going to calculate prime numbers. Okay, so I am very sorry. Do you know what a prime number is, my friends? Do you know the definition of a prime number? What is a prime number? How do you define a prime number? Now, actually, you can see the definition. A prime number is a positive integer which is greater than 1 that is not a product of 2 smaller positive integers. Okay, 2 smaller positive integers. For example, 17. 17 is a positive integer that is greater than 1, and it's not a product of 2 smaller positive integers. It's a product of 1 and 17, obviously. When you multiply 1 and 17, you get 17, but 17 is not smaller than itself. Therefore, it is not following this definition. Therefore, we say that 17 is not a product of 2 smaller positive integers. Therefore, it's a prime number. Okay. However, 15 it's not a prime number because 15 can be expressed as the product of 2 smaller positive integers like 3 and 5. When you multiply 3 and 5, it's a 15. Therefore, 15 is not a prime number. Another definition for the prime number is this. Again, a positive integer that is greater than 1, which can be only integer divisible to 1 and itself. Okay. So it's not going to be integer divisible to any other positive value other than 1 and itself. Okay. So 2 is also a prime number, my friends, because by this definition, it's true. 2 is greater than 1, and it's not the product of 2 smaller positive integers. 2 is the product of 1 and 2. Therefore, there is no other 2 positive integers which will yield us 2. Therefore, 2 is also a prime number, which means the first prime number is always 2. Okay. We also know that the other prime numbers are 3, 5, 7, right? Then 11 we have, then 13, then 17, 19. It goes like this, 23, I guess, the next one. So these are the prime numbers. Now, in our program, in the next program, we want to create a list of 20 smallest prime numbers. Okay, the program will terminate once we create a list of 20 smallest prime numbers. So we say the first prime number is 2. P0 is 2. The first prime number at 0 index is 2. And the n value is 1. And we say PC. PC is the prime candidate. It's a candidate, my friends. Okay, PC, prime candidate. 3 is the next prime candidate. We will check whether it is a prime number or not. 3 is a prime number or not. So P0 is the first prime number, P1 is the second prime number, P2 is the third prime number. It will go like this until we create P19. In that case, we will be calculating 20 small. We will be calculating 20 smallest prime numbers. And every next number after the last prime number will become a prime candidate. We will check whether it's a prime number or not. Okay. Now there is a diamond shape here again. N is current one. Right now we only have one prime number. Until the total number of prime numbers we have is 20. So as long as n remains less than 20, as long as the prime numbers that we have evaluated remains less than 20, we will move in this direction. Otherwise, we will simply return the list of the prime numbers from the 0 index to n minus first index. So when n becomes 20, we will get P0 to P19, 20 prime numbers. Otherwise, we set I to be equal to 0, okay, I to be equal to 0, which is an index. If I is less than n, if I is less than n, we will just move this direction and we will divide the candidate prime to existing primes, okay, Pi. I is 0. Right now we only have 2 as the prime candidate prime numbers. So we will divide that value to 2. When we divide that value to 2, if it's a positive integer, which means if it's integer divisible, then we will update I as I plus 1. Okay, we will move to the next prime number basically in the list. And if I reaches to n, if we reach to the current prime numbers in our list, the total number of current prime numbers in our list, in that direction, in that case, we will move to that direction. Now, I am very sorry, I have misleaded you here. If prime candidate is integer divisible to prime I, we move to this direction. If it is not integer divisible, then we check whether it is integer divisible to the next prime candidate. Okay. Now, for example, 3 is not integer divisible to 2. Then we need to check the other prime numbers in the list. If the prime candidate is not integer divisible to all prime numbers in the list that are existing previously, then it must be added into the list as a prime number. But if somehow, please check, if somehow we can find a prime number in the list which can integer divide the prime candidate, in that case, we make I equal to n. Okay, in that case, we enter into another decide module here. And we say if I is equal to n, okay, if all prime candidates are checked, or if we find a prime candidate which is not dividing, which is integer dividing the prime candidate, then we say update the prime candidate as prime candidate 1. Okay, so if we say that if somehow that prime candidate is integer divisible to 1 value in the prime numbers list, then it cannot be a prime candidate anymore. We move to the next prime candidate, like for example 4. However, if I is equal to n, if we have all checked all prime numbers, okay, if we have checked all prime numbers and none of the existing prime numbers can integer divide that prime candidate, then we say the next prime candidate Pn is Pc. The prime candidate becomes a member of the list prime numbers. Then we update n as n plus 1 to calculate the next prime number. And the next prime candidate will be the incremented version of the last prime candidate. It goes like this. So there is a very complex mechanism here that you need to analyze at home. It may not be very easy for me to explain in the first time. You can just follow this structure, okay, for each case. You will eventually realize that this flow chart works perfectly to return us n prime numbers. All right. So this is the code that we are going to do. Let's check it, 06. So let's explain it here. My first prime number is 2, which I include in my initial primes list. And the next candidate is 3. The next candidate is 3. PC, basically, prime candidate is 3. Basically, I will check every integer starting from 3 until I get 20 prime numbers contained in this primes list. I say, while the length of the primes list is less than 20, while I reach to the necessary length, okay, this while loop will continue until 20 primes are collected in this list. I say I, which is index, remember from the previous flow chart. Sorry, in the previous flow chart, there was a I here, which is my index. I set index at 0, and I say, while the index is less than the length of prime numbers, this index will iterate over all prime numbers, okay? I will increase index, increment index at every iteration. So index will be iterated over length prime numbers. In fact, we could have done this instead of using a nested while loop, but we can use a for loop here, okay? The index can be defined over a range object, which is taking integers as indices of the primes vector. So we can write range, length of primes here, and the index can take these values by using a for loop here. But here we are using a while loop, and we say, if the next candidate, which is 3 right now, is integer divisible to the prime number at index, okay, the at index here. If it is integer divisible to that, then I break out of the while loop, which means that prime candidate can never be a prime, okay? However, if it does not, it is not integer divisible to that prime number in that list, then I increase the index by 1, and I check if it is integer divisible to the next prime number in the primes list, okay? Now, out of this while loop, either we break out of the while loop by finding the fact that the candidate is integer divisible to one of the prime numbers, or it can basically check every prime number currently is in the list, and we realize that it is not integer divisible to any of them. In that case, the index will reach to the length of the primes vector, and again, it will terminate the while loop, okay? Now, in the end, if the while loop terminates by incrementing the index successfully to the length of the primes, which means it can check every primes number and the prime number in the primes list, and it realizes that a prime candidate is not integer divisible to any of them, so that the index can be incremented to the length of the primes. In that case, we append that candidate to the primes list to become a prime number, okay? Now then, after this if statement, we check, identify the next candidate. For example, after 3, the next candidate will become 4. So until, in total, the primes list will become at a length of 20, the outer while loop here will terminate, okay? The outer will execute itself, will repeat itself. Then I can print primes, and I say that you have listed first 20 prime numbers. So let's check. It's worked successfully. So the first 20 prime numbers are some primes from 2 to 71, and we have listed 20 prime numbers here. Now, if I change this 20 to 30, I will get 30 prime numbers, okay, until 130. In fact, I can make it 300, and I can get 300 prime numbers. My friends, prime numbers are infinitely many. So there is no last prime number. There's a very, very significant mathematical proof for that. Prime numbers are also they continue infinitely. Above every last prime number that we have discovered, there's also another prime number. Okay, therefore, you can write a large value, as large as you want, like 3000. Again, our program will execute, okay? And you will be listing 3000 prime numbers here, okay? The 3000 prime number is 27,449. Okay. Did you understand this loop, my friends? It's a nested while loop. There is one while loop inside another. Did you understand? There will be a question like this in the exam. Let me tell you that here. Not necessarily related to discovering prime numbers, obviously. Yes or no, please? Did you understand? Because I'm going to move to the next page.
Yes hocam.
Okay. Now, in this next example, I am just going to update my previous program such that the length of the primes list will be provided by a user. So the user will tell me how many prime numbers that he is interested in. It will be converted to an integer and the program will generate a list of n smallest prime numbers. So we are just going to combine our last two programs as in the next program. So I'm not going to explain it on the present spider. So I write again a while loop. That while loop will try to execute the try block every time it repeats. However, if a value error exception occurs by the input that the user provides, it says please provide an integer. Otherwise, if the user provides really a positive integer, which is converted to integer successfully, and we say there may be an error here, list length. Okay, it will be assigned to the list length. If the list length is negative, then it will be asking the user to provide a positive value and the loop will repeat itself. Otherwise, it will break and will take the input that the user provides. So you can here in this program, you can enter how many prime numbers that you want to see in your program. Then the second program will loop until the length of the primes list is equal to the list length that is provided by the user in the first while block. Okay, so the rest of the program is the same as the previous one. Now let's check it here. First, in the first while loop, the user needs to enter something. I write I'm Batman. It says please provide an integer. I write -2. It says please provide a positive value. I write, okay, I know what I want. I want 500 prime numbers. Okay, then when I press enter, I exactly get 500 prime numbers as the last prime number being 3,571. Okay, so now this program is a flexible program which returns us actually the number of primes, a list of primes, which is defined by the size of which is defined by a user input. So that's it, my friends. Now, I'm just going to make some remarks and finish my lecture, hopefully. And thank you for listening, by the way, and participating at this early class hour. Right now, I have 18 remaining students in class hearing my teaching here synchronously, and I just want to thank for all of them because your existence is motivating me in this Saturday morning, and weather is very good, by the way, in Istanbul. So let's just follow the last remarks. Now, my friends, comprehensions that we have covered today, list comprehensions, set comprehensions, and dictionary comprehensions, they are imitating for loops only, for loops. If you check, so let me show that part. If you check comprehensions, you only have 4 structures or 4 keywords in it. Okay, unfortunately, there is no comprehension structure. There is no comprehension structure in Python which imitates while loops. So basically, comprehensions are imitations of for loops to create list objects, set objects, or dictionary objects. But you cannot create a list object by using a list comprehension, which is driven by a while loop. Okay, but it's possible to write one. Okay, you can write a function, for example, or a class, basically, which we are going to learn later on. You can write a class which is going to be an imitation of the list comprehension over a while loop using the keyword while, but it requires a very, very advanced knowledge. Okay, in built-in structures, comprehensions are just following the for loop mechanisms. Okay, not while loop mechanisms. This is why we have taught comprehensions before the while loops. Okay, because the comprehensions are just imitations of for loops to create lists, sets, or dictionaries. This is the first remark. Second remark. In any language, there is not only a single way to express this statement. So there is a statement here. If it rains, the ground gets wet, right? If it rains, the ground gets wet. If the ground is dry, it means it does not rain. So these two expressions are the same. Now you know it from discrete mathematics. If P is Q, then not Q is not P. Okay, or in other words, if P is Q, okay, then if not Q is not P. Okay, we say it like that. If it rains, the ground gets wet. If the ground is dry, that means it does not rain. Now, just like in mathematics, in Python, there is not a single way to implement a certain algorithm. You are basically creating a perfect working program. As long as it is error-free, there may not be any error in it, any type of exception, or any type of logic error. It must not contain any type of error in it, and it should work as intended. It should basically give the result as you have designed it to do so. Okay? It should be free of unnecessary calculations. It should not calculate things unnecessarily. Okay? And it should be free of unnecessary memory allocation. For example, in order to return the 50th number of the Fibonacci sequence, it was not necessary to exactly create a list of a Fibonacci sequence with 50 elements. If you remember from the last time, we were just working on the last two values that we have evaluated in the sequence to create the next one. And we were updating the last two values in the last while loops that we have written. And actually, the last version of it was free of unnecessary memory allocation. And it should be free of unnecessary calculations so that your program can be minimal in computation time. So these four properties of a program: it should be error-free, it should work as intended, which means it does not contain any logic errors. If it is not doing any unnecessary calculations, or redundant calculations, and if it is not using unnecessary memory space, then your program is a perfect program. Okay? But you can implement a program in many different ways because language is flexible. Programming language is flexible. It does not matter which structures that you use, objects, loop mechanisms, either use a for loop or a while loop, or you use a try except block or not, or you use if blocks or not. It doesn't matter. As long as your program satisfies these four properties, it's a perfect program. Okay? The last program that we have written to evaluate a list of prime numbers, first k prime numbers, let's just say, could have been written in different ways. For example, I have told you that this inner while loop here can be replaced by a for loop. So it doesn't matter whether you use a for loop here or while loop. You can at home, for example, as an exercise, you can check how you can change the inner while loop into a for loop. Usually it is they can be converted into each other, but sometimes they are not. Okay. Remark 3, a good programmer needs to know how loop mechanisms, if else, if else blocks and try except blocks can be efficiently nested to achieve the flow of control in a program. This competence can be gained only by more and more practice. So at home, if you do not try to solve the exercise sets given in the regarding module here, okay, the exercise set 8. If you do not do that, you will not be able to get prepared for the exam. Okay, I mean, you need to write these codes in exercise sets. Okay, you need to basically practice, challenge yourself with these practices so you can better understand how you can nest loops, if blocks and try except blocks into one each other. And the final remark is what? The imperative knowledge that you have gained in operations research fields, such as optimization algorithms, simulation modeling, and heuristic methods. Okay, so you are just going to learn so many things in the future, my friends. Okay, right now in operations research class, you are learning about the simplex algorithm. In 325, you will learn about simulation modeling. In 343, you are going to learn about heuristic methods. Okay, there will be several courses that you are going to take about operations research. Okay, now in these courses, your lecturers may not assign you homeworks in which you actually need to use a programming language. Sometimes the students are selecting courses, especially in which the lecturers are not assigning any homework related to a programming language. This is basically a weak way of making decisions, okay? Sometimes the lecturer may not ask. For example, in 325 simulation, I am not actually asking students to write any program by using a programming language. My applications are either in Excel or a simulation software that is called Arena, okay? However, every once in a while, it is best for your future practices to ask yourselves, can I implement this method in Python? And try to do so to expand your knowledge. Because if you do not use your programming language learnings in this course, after this course, in 2 years of time, when you graduate, you will be asked to do so in your senior design project. And during the senior design project, every student tells us this. It's just been 2 years since we have taken a class related to programming languages. So in these 2 years, what have you done? Now, even if the lecturer do not assign you a homework about the programming language that uses a certain programming language, I think you should strengthen your programming language by thinking about how you can implement these methods that you have learned in your future classes in programming languages. In the area of computation and data science, my friends, knowledge and practical competence in at least one programming language is a necessary attribute for a successful engineer, my friends, okay, who can really solve sophisticated problems. This warning is important. So you should always have an idea, just like you know English. English is a good attribute to an engineer, right? So an engineer who does not speak English, I think it's not a good engineer. Just like that, an engineer who cannot implement the solutions to his or her problems in a programming language is not a good engineer either, okay? However, your mind, if it remains weak, your mind will always discourage you about this. It will always say that, do not take any course in which a programming language is going to be used. Do not try to code this in a programming language. You can do it in Excel. Do not discourage yourself about Python. Try to implement your solutions using programming languages so you can get better, and you will definitely be rewarded by the fruits when you search for jobs, okay? So a good Python knowledge will actually bring you a good job in the future, which pays a lot of money. Therefore, my recommendation to you, not just in this class, in your future classes as well, try to use Python as well. That's it. This is the end of the lecture slide. In the first midterm exam, my friends, you will be responsible up to this point. Okay, this is the last point where you are going to get questions in the first midterm exam. That's it. I am just going to stop recording.